let's do a few things to solidify some of what went on in the last lecture. Share the screen. So what I had talked about last time were the differences between GLS and ML. So if we're taking a look at a data set that has the four variables that are presented in the chapter, this is what the correlation matrix looks like. And if you want, inside of AMOS, this is also another example of how you can input summary data if you're analyzing someone else's correlation matrix. You can specify the covariance matrix and as follows, or you can say it's a correlation matrix and put in another line of standard deviations, and it will figure out the variance covariance matrix for you and the adjoint sums, squares, and cross products matrix. But as we mentioned here, we have four variables. One is a correlation of 0.8, one is a correlation of 0.7. And what I'd like to do is to fit a model to the data with these four variables, and just for the heck of it, we can move this around quickly, and we can come into our data set variables and we can drag them over into the manifest indicators. And then if I wish, I really wish there was a way to get up at the top of that, but Zoom hides that for me. I can name the parameters in the model. Generally speaking, I like to use the letter L for loadings. And I can come in and I can name the unobserved variables. And that will give me this diagram to look at. And my point was, inside of AMOS, I can come now into the analysis properties and look at the estimation. And I can say, give me an unweighted least squares solution. And I can hit the run button. And by the way, let's go into the output. And I want to take a look at the implied moments and the residual moments and the sample moments. That is, I want to see the correlation matrix echoed back to me. And I also want to see what the values of the implied correlation matrix are. So I can hit that run button, at which point I have some numbers. And I can look at my output. And down here underneath the estimates, I've got the loadings that I have, but I've also got the matrices. So notice that under regular ordinary least squares, I don't, it's a misspecified model. It's not a perfect fit, but it really captures that 0.7 correlation and ignores from the 0.8 correlation under least squares loss. And this is because it's trying to do a job of looking at the absolute difference between the observed correlation matrix and the predicted correlation matrix. And these numbers, I mean, V1 through V4, it's kind of in reverse order here, but these numbers match what are in the book. If I want to go back to the analysis properties and say, now I want to do a maximum likelihood estimate, I click this button, and I can re-hit the run model, and I can look at the estimates in my model, at which point my implied covariance is now 0.8 here. This is a correlation between 1 and 2. And I don't do that great of a job analyzing the other analysis. Notice instead of 0.3, I've got 0.2 for these correlations. So rather, I'm really going to mess up my estimate of that 0.7 correlation, but these numbers are going to be MLR closer to the true values in the model. And that's the object of the illustration, that these loss functions, by incorporating a weight function, give you slightly different answers. As a little bit of an exercise in AMOS, I can come back to this model, select everything, and use this little bus figure to move variables around should I wish. The other thing that's somewhat handy inside of AMOS is it gives you control over the particular elements of your diagram look. So you can come into the drag object properties, and you can then select from any of the following properties and carry those forward. So for example, let's say that I don't like this square and I think it's too small. So I can come in and click the Shape of Objects button, and I can make that object a little bit bigger. Oh, actually, when I do it with the draw the latent variable, it changes the size of all of those things. But say I also wanted the same size roughly to apply to the error variables. So I come in here and I can say the height and width of one of the properties should be carried forward to the bottom one. So after selecting these two, I can come down here and drag down to this, and it will change the size of that. And that's kind of nice. And then if I want, I can, carry that forward over here. And that way you don't have to sit there and futz around with trying to make things exactly the same size. Similarly, if you want to have everything be at the same height, you can have the same y coordinate by dragging things. This one isn't messy as at the time, so it's not really necessary. And if you want to have the parameter positions be the same and so forth, these are other things that you can do to affect that. So that's just a little how-to, showing some more things that you can do inside of AMOS. I wanted to take a moment and rehearse what we're talking about in terms of our loss functions and wrap up the discussion here. That least squares loss function is an easy thing to understand. For structural equation models, we generally do not use it because it doesn't pay attention to the strength of association between variables as much as one ought to. It really wishes that you could capture the strongest relationships well. And a difference between 0 and 0.2 isn't that important. After all, if you square the 0.2, you're looking at 0.04% of the shared variance between variables. And if you square 0.8, you're looking at 64%. So it's better to recover where the stronger relationships are in your data set. That computationally speaking, looking at the magnitude of the association can be done by referring to the predicted variance covariance matrix at a given iteration, or by looking at the data that you have. And generalized least squares is looking at the observed variance covariance matrix, and ML is looking at the strength of association based on the parameter estimates. ML is a little more computationally intensive. You people are the beneficiaries of advances in computing power, so you don't really have a problem there. Hold on just a minute, I'm going to turn the heater off down here. In very infrequent cases, you might find some problems with ML estimation because the particular values of the parameter that you just happen to have at that iteration result in a predicted variance covariance matrix that can't be inverted, that the determinant is 0. That's a very infrequent problem in advances in the software. Generally, I haven't seen that crop up in now probably 5 or 6 years, but it can happen. ML is a little more computationally intensive there. So Anne had talked about, what's this stuff about when you have categorical dependent variables the last time. And weighted least squares is an attempt to adjust the variance covariance matrix for the magnitude of the variances that are estimated when that manifest variable is categorical. And that's more or less where I left it last time. And we'll get to this toward the end of the course when we start talking formally about categorical dependent variables. But for the moment, what we can say is when you have a categorical variable that goes 1, 2, 3, 4, 5, you don't necessarily need to treat that as a continuous variable. You can say, well, 1 means something, 2 means something, and 3 means something, and the spacing between those numbers may be different. And we take as our clue about the shape of the underlying distribution by the frequency counts of those various categories. So you might observe a frequency distribution and say, well, maybe this reflects an underlying normal distribution or an underlying logistic distribution. And that type of assumption in the data means that you need to adjust the assumed variance and the assumed covariances in the data. Olson in 1979 said, well, let's just take a correlation matrix that's pairwise adjusted for everything and estimate a common set of what are called thresholds. And again, at the end of the class, we'll tell you what a threshold is. And basically that weights the estimates of the variance covariance matrix for the means and the variances of the variables. If you're looking at things like M+, that uses a limited information approach that's a little more computationally efficient, and it's called diagonally weighted least squares. So in terms of, for you as a user at this point, when you tell M+, hey, this is categorical, it's going to go out and do a slightly different estimation. At this point, we'll get to the guts and the details of the ins and outs of that later in the class, but that's what you need to know at this point. You can still hit the run button and you can still look at your printout. One thing you need to know is that when you use that type of estimation, the formulae for standard errors and the fit statistics are no longer appropriate. So we can't interpret the standard errors as we normally would if we had continuous data. So the tests of the parameters that are based on a wall statistic really don't apply. So inside of M+, they'll do some robust estimation procedures in the background. So you can look at your printout. Other programs, though, are not there yet. So the robust approaches and tends to work well with smaller samples and certain types of non-normal data. There's another way of doing the estimation. So M+ and other packages will default to diagonally weighted least squares. If you happen to have a smaller sample, and if you happen to have missing data, you may want to consider maximum likelihood robust estimation instead. Even if you have continuous variables, you may want to explore MLR. So rather than saying estimator equals ML, you say estimator equals MLR. These are not options that are available in AMOS, by the way. And the nice thing about maximum likelihood is it does have some nice connections to missing data. And it might be preferable in many situations for that. So at this point, I'm going to have to, given that we're just opening the box of confirmatory models, I'm just going to leave this discussion here and say, in addition to maximum likelihood, there are these other things when you have categorical data, and if non-normality and missingness is an issue, MLR might be something you may wish to look at. So that covers, in this chapter, an awful lot of territory, ranging from start values and how start values are iteratively improved until you get final values and things are hopefully converged, the issue of random starts as being a way of containing the problem of local optima, and then moving to loss functions, which are the object of the minimization, but also give you some opportunity for choices about different loss functions that you can look at. And so this is a nice place to say, are there any questions? So let's wrap up the chapter and say, well, even though we've done all of this work of fitting a model, it's always good to go back and look at the assumptions of the data. And I thought it's good to model that with the example in the chapter. So in this, if you look at the observed correlation matrix and the predicted correlation matrix, you might find that there are particular parts of that model that don't fit well. So you can look at the observed and predicted correlations. In this case, maybe looking at the inspection of that would motivate the thought that maybe you want to consider making some local adjustments to your data. So in this particular case, looking at the one-factor model, it seemed like the relationship between alcohol use and 5+ drinks wasn't particularly well modeled. So I added an additional covariance downstairs here between those two terms. That improves things. It's an arbitrary change. I could just as easily have said, I will not have a correlation between these two things. Maybe given the fact that all three of these variables have to do with last week, I'll add in correlations here. That involves adding 3 parameters to the data rather than just 1 parameter. So maybe it's not parsimony. On the other hand, maybe conceptually you'd want to do that because all of these 3 things are just what happened in the last week. And maybe a big football game happened or a birthday party happened or something that might cause these things to be correlated. It's also good to go back and look at your influential observations. So in these cases, I looked at the influence diagnostics for the data and found that if I look at the influence diagnostics, actually these loadings change rather substantially. So here are what the loadings look like based on the complete data, and here's what the loadings look like if I exclude influential observations. Well, notice this standardized coefficient changes quite a bit from what it was in the raw data set. So the reason that this loading goes down is you've got some individuals in there who are partying very hard across all 3 days. And that's not typical of a general factor of alcohol use. It might be the case that Saturday drinking is kind of its own thing that's distinct from drinking in general or across all of the variables. And similarly, I can look at the difference between the unstandardized and the unstandardized regression weights with and without those values. Third thing is to come back and look at the functional form. So again, I can save the factor scores out of my model, and I can plot the alcohol use factor score as an X variable and one of the variables, manifest variables in my study. And the low S curve is shown here. It kind of bends off, and over here, I have a straight line. Well, we scratch our heads a little bit and say, well, why did that happen? Well, perhaps some of the reason that that happens is I have a large number of individuals who last Saturday reported not drinking at all. Perhaps that's a distinct population. Maybe I want to write up my study and say, well, actually what I'm going to look at is the relationship between these manifest variables among students who report drinking at least something. So we know that women are less prone to drink. We also know that a proportion of the population at Mizzou are abstainers as freshmen for religious or cultural reasons. So if I rerun the model and I throw out these people and reestimate the line, that relationship looks a lot more linear. The other thing to notice about it is the slope of that line is a lot steeper than include, what happens when I include them? Well, the slope of this line is your factor loading. So dropping out abstainers in this particular study is going to give me a factor loading that's a lot larger, as well as perhaps a lowest regression that looks a lot flatter than it would otherwise. So this is an example of, and this is why you might want to do this. Questions on this? I mean, and I summarize those things as well. Okay, well, let's turn to a discussion of model fit. And the summary statement here is that whenever your model has fewer parameters than you have elements of the variance covariance matrix, you will not be completely reproducing the variance covariance matrix in your data. It's an example of what Karl Popper called, science is the use of descriptions of nature that omit details of what nature really is. It's a close enough explanation. And when you're looking at structural equation modeling, you're going to see that there is a variety of fit measures, and there'll be a chi-square test going on. In order to communicate how that gets built and why it is that you have more than one fit measure that may help you decide which model wins, it's necessary to do a little bit of review of what we call asymptotic theory or exponential theory. And this is not scary. This is a way to build connections with other statistics classes that you may have had. So, having to watch myself on the videos, I'm trying to limit my use of the word so, because it really annoys me when I have to listen to myself again. Let's consider a normal distribution here. We have the mean of 0 and a standard deviation of 1. And what I'm going to do is I'm going to take an observation from this distribution and I'm going to square it and I'm going to plot the results. So a value that's very close to 0 is, well, asymptotically not going to happen at all, but there'll be a lot of observations that are close to 0. And when I square them, I'm going to get this distribution out, this value. And observations very far from the mean are going to happen very, very infrequently. And when I plot those out, those are going to happen way over here. And the resulting distribution is going to have this shape. It's going to be skewed to the right. This distribution has a name. It is the chi-square distribution with 1 degree of freedom. It is, as we're going to see, it's going to have a really nice relationship with the maximum likelihood loss function. But for now, the first thing that I will want to say is this chi-square distribution is a continuous distribution, and it has nothing whatever to do with categorical data. As a matter of fact, I did an article a few years ago that talks about Pearson's x-square. People often refer to that as Pearson's chi-square, but it's really not a chi-square. And if you read his original manuscript, he does not use the Greek letter chi. He just said, this is a distribution for contingency tables that kind of looks like a chi-square. But this resulting distribution, the chi-square with 1 degree of freedom, is going to have a mean of 1, which, as we're going to find out, is going to correspond to the degrees of freedom. It's a 1 degree of freedom thing. And it's going to have a variance that is equal to 2 times 1, or 2 times the degrees of freedom. Does that work? And one thing you need to know about this is that it's never possible for you to ever get a chi-square value that's a negative number. Mathematically, it cannot happen. And when inside of your model comparisons that we'll be doing with SEM, you see a negative number, that's a problem. It means somebody is maybe in a local minimum, or some error has been made in the computation. And these things can happen. So that's why I take the time to say negative chi-squares can't happen. One of the cool things about the chi-square distribution is that it is what we call additive. That is, I can repeat the process over here. I can take a distribution of normal distribution and make a chi-square distribution. And I can make another one and have another chi-square with 1 degree of freedom. I can take an observation from here and add it to an observation of the second distribution, and the result will be a chi-square with 2 degrees of freedom, as shown here. Well, the resulting distribution is going to have a mean of 2 degrees of freedom, of 2, and a variance of 4. And notice what's going on, that if I would repeat this process and do it yet again, say, take an observation from a chi-square with 2 degrees of freedom, and add that to another observation drawn from a chi-square with 2 degrees of freedom, that's going to give me a chi-square with 4 degrees of freedom. Well, the mean is always going to be equal to the degrees of freedom, and the variance is always going to be equal to 2 times the degrees of freedom. And as I repeat this process more and more, notice what's happening to the shape of the distribution. It starts out really skewed, and the more observations I draw, the more and more symmetric this distribution happens. As a matter of fact, if I kept doing this a lot and a lot, there's something called the law of large numbers that says as chi-square degrees of freedom go to infinity, the resulting distribution looks like a normal distribution. So I feel needy. It's Friday. Is this clear?
I have a question. Why degrees of freedom equal to mean?
Why did I what?
I said, why the degrees of freedom equal to mean?
That's just how it works out if you do the math. So the nice thing about it is that if you start out with the normal distribution and I draw observations from it and square them and plot the resulting distribution, that thing is going to have a mean of 1. Well, you can know kind of intuitively that if I take numbers here and I square them, I'm going to have a positive number. What's unknown is, what that positive number is exactly going to be. So for the moment, we'll believe statistics people when they say, oh, the mean's going to turn out to be this and the variance is going to turn out to be this. But the important parts here that the takeaway messages are here. First of all, chi-square has nothing to do with categorical data. Secondly, chi-square distributions can't be negative. And third, if I draw from a chi-square distribution and I start adding the 2 numbers together from draws from that population, the result is also a chi-square distribution. And the more times I do this, the more the mean increases and the variance, but the more symmetric that distribution becomes. So that's a summary of my major points. All right, now we're done with the scary asymptotics here, distributions. There's only one more term I want to add to this. This is called a non-central chi-square distribution. And the reason you care about that is sometimes when you're doing assessments of power for structural equation models, you need to know what this is. It's a straightforward extension of the central chi-square distribution you have here, except that before you square these variates, you're going to add a constant to the variable. So, for example, I might say I'm going to take an observation, maybe it's -2, and I'm going to add 1 and then square it. I'll take the 2 here, I'm going to add 1 and then square it. So that would give me values over here of, instead of 2 squared is 4, I would have 1 squared is 1. And over here, I'd have 2 plus 1 is 3, squared is 9. So the resulting distribution is going to look different than this distribution. And that's all we need to know. The sum of the squared means of across all those variables is called something called a non-centrality parameter. And we use the letter delta for that. So if you want to figure out what delta is, it's going to be the sum of the squares of the values. So for example, here we have a chi-square with 3 distributions, and over here we have a non-central chi-square. And with my central chi-square distribution, here's the distribution that looks like. And here's my non-central chi-square with a delta of 3. When your model does not fit, that's going to correspond to, the degree to which it doesn't fit. It's going to have a certain non-central chi-square associated with it. When your model does fit, it will be drawn from a central chi-square. So when we're designing our study and we're setting our alpha, in this case maybe a 0.05, the power to reject a model is the area under this part of the curve. If you're looking for a numerical way of estimating what the power is of one model versus another, so the theory goes, you'll need to specify a model that's false and say, well, the shaded area under this part is my power to reject the null hypothesis of a particular model when it is false. This is meant to make some connections with things you may have already heard about statistical power. It's a topic that is worthwhile to address in this part of the handout. It's not something that we're going to be covering much in this chapter until the end, but I put it in here for putting everything about distributions in one part of the handout. So let's talk about model fit. Well, one of the cool things about SEM is that fit function for the maximum likelihood value. If I multiply it by the sample size -1, and the null hypothesis is true, that fit function is going to be distributed as a chi-square distribution with degrees of freedom equal to the difference between the number of unique elements in your average cross products matrix and the number of free parameters in the model. So, for example, if I'm looking at a regression model or an ANOVA model, I have exactly the same number of parameters in my model as I have elements of the variance covariance matrix or a joint sums of squares and cross products matrix. Chi-square is going to be 0 with 0 degrees of freedom for that. If, however, I'm fitting a factor model and I have fewer parameters than I have elements of the variance covariance matrix, the multiplying the fit function by the sample size -1 is going to give me a chi-square distribution with degrees of freedom equal to the difference between the number of parameters and number of unique elements. What this means is use of a chi-square test is that it is a test of poor fit. And I guess it's a source of minor frustration on committees and some extended manuscripts when researchers will say, I did an SEM and my chi-square is very, very significant, so I know this is great. It's not good. If you were using the chi-square test as a model fit, you want to see a small value. You want to see non-significant chi-squares. This also addresses power, because if you have an SEM with very few observations in it, you're not going to have great power. A model could be lousy, but just because you only have maybe 40 or 50 people in the study, chi-square is going to be non-significant. This does not necessarily mean that you have successfully captured everything in the data. On the other hand, large samples are also going to result in you finding statistically significant chi-squares. First of all, part of this is due to the fact that that test is telling you the odds that your data could have occurred given the null hypothesis and all the other assumptions of the model. And the problem is that God might be telling you not that the null model is false, but that it's the case that your data are not conditionally normally distributed. Or there may be small numbers of influential observations in the data. So for example, what we had talked about earlier on this model, that has a significant chi-square, but that's not an indication that the model's bad. It's an indication that something else about this model isn't quite right. We said there are influential observations or maybe a nonlinear relationship. In this particular data set, notice that we had a significant chi-square, but if I throw out the influential observations, all of a sudden now my chi-square goes down to 3, and it's no longer significant. So as you're looking at this, you can't just interpret that standalone chi-square. Maybe small departures from normality are also giving you a significant chi-square. So this led to research on the part of people to try to find some other summary measure of structural equation modeling that would tell us if something is fitting well. Now, one of the earliest things that made some sense to people was to take the chi-square in your model and divide it by its degrees of freedom. And, to some extent that might work. The chi-square divided by its degrees should be a number that approximates 1 if the null hypothesis is true, and it should be some number a lot bigger than 1 if it's not. So in your printouts, you may see chi-square divided by degrees of freedom, and that's what it's doing. That's a general method. What we'll do now is to talk about, we won't get through it all today, but we'll talk about the rationale for various measures of fit. One way of approaching this is the standardized root mean square residual. And we often use this little abbreviation. There are some people who enjoy this model because it intuitively talks about the errors or the discrepancies between a model's variance covariance matrix or correlation matrix and what happened in the data. The idea is pretty straightforward. In other words, the measure is exactly what it says it is. I'm going to calculate the residuals, the difference between the observed and expected variance covariance matrix. I'm going to square them. I'm going to take the average of them, and I'm going to take the square root of that. and we'll employ a little standardization to take into account the fact that I'm dealing with a variance covariance matrix. You will see that in printouts, there are some rules that people have suggested for having a good standardized root mean square residual. Barbara Burns' books that I've mentioned before say, well, if you have a value less than 0.05, that's nice. Hu and Bentler published an article where they recommended use of 0.08. Their article also went on to say, if I've got a value greater than 0.09 and a comparative fit index less than 0.6, it's not very good fit. It's been kind of kicked around by somebody else saying that maybe that recommendation is an artifact of the particular types of models they considered in their article. But if you're looking for, when you write things up, here's my value, is it good or bad? This paragraph seems to be the state of the art in interpreting what numbers are good and bad. It is not generally used as a standalone fit measure these days. So to cut to the chase, or to know what you want to be paying attention to, we often look at the TLI a little bit more and the CFI and the Rmsea, but we'll get to those in turn. It's helpful, though, to know what the rest of your fit measures are so you can compare and look across printouts. The Rmsea is another measure. It has an advantage that it also gives you a confidence interval. And for the Rmsea, low values of the Rmsea are indicative of good fit, and high values are indicative of poor fit. Well, the Rmsea, in general terms, is a measure of our old friend, the non-centrality parameter of the chi-square distribution. I see I need to put in a Greek letter there. And it's adjusted a little bit to take into account the sample size. So I'm going to take the chi-square for my model minus its degrees of freedom and take the larger of the two numbers. And this rescaling is taking the delta and then dividing it by its sample size. One of the frustrating things about statistical software is sometimes the equations vary just a little bit, and you might find a different Rmsea number from one piece of software than another. M plus uses a slightly different formula, dividing by n. And the final, and that gives me my delta, the final value of the Rmsea is the square root of the delta that I have up here or here, and divided by its degrees of freedom and taking the square root of that. Low values of the Rmsea are indicative of good fit. And now we have a fight about, well, how low does it need to go? So some people like to look at values of 0.1 or less. Steiger and Brown suggested less than 0.05. And McCallum, Brown, and Sugawara said 0.05 to 0.8. Everybody seems to agree that values of 0.1 are poor or fair fit. And Chen and others argued that, looking at it, you really kind of need to look at the particular model you're looking at. My advice to you is the Rmsea is probably interpretable relative to the substantive area that you're looking at. For example, if you're looking at behaviors that are extremely well defined, say cigarette use, or things like verbal ability, or standardized tests, you can probably get by, you will probably observe Rmseas that are very, very low. If you're looking at something that's less well-defined, less reliable, less internally consistent, Rmsea values that are on the larger end are probably okay. So in some areas of social psychology, say mindfulness or priming effects, it seems that our models don't fit back down to the really, really low values of the Rmsea. The Rmsea also has the advantage that it's going to give you a confidence interval. So if you have a relatively small sample, the confidence interval will be wide, suggesting some caution to you that even though my Rmsea was low, it could be that, you know, in truth, if I had more observations, the Rmsea might be poor. The 0.05 cutoff value that was mentioned above for good fit also led to the calculation of something called the probability of close fit. So it's an estimate of the probability that the Rmsea is 0.05 or less. So again, if you've got a really low Rmsea, you're going to have a probability of close fit that's large. And I talk a little bit about the fact that, you know, the magnitude of that confidence interval depends upon your sample size. There are some cautions. Kenny, Kanaskin, and McCoach said, you know, you shouldn't be looking at the Rmsea if you have small numbers of degrees of freedom in your data, if you've got something that's really close to a just identified model as it stands. So the Kenny article said, you know, what you really probably want to do is to test the Rmsea in the presence of what's called the independence model, or a model that assumes that all your variables have zero covariance, before you start interpreting your Rmsea if you have a small degrees of freedom model. It's close enough to the end that this is probably a good stopping point. And what we'll do next time is I'll go through chi-square difference tests and explain to you what this independence null model is and how the idea of an independence null led us to the calculation of other fit indices that are roughly scaled on 0 to 1, where high values are indicative of good fit. And inside of that, we have things like the TLI, the CFI, and the norm fit index. Right. Any questions here?